So to make sure that we made this clear, right? In the example A, the urine concentration was 0 as expected, so the clearance was 0 milliliter per minute. While in the example B, the clearance was 25 milliliters per minute. There was glucose in the urine because the filtered glucose is reabsorbed by carrier proteins because glucose cannot cross the plasma membranes. It gets filtered through the slits and the fenestrations, but it cannot be reabsorbed by carrier proteins. It can only be reabsorbed by carrier proteins, and once you saturate the carrier protein system, then it will not reabsorb it anymore. So when the plasma glucose levels are high, such as, I was supposed to ask you the question, but such as in diabetes or hyperglycemia in general, then that is a sign of a disease. So we're going to talk about the tubular transport in great detail next week. So for now, just be happy with knowing that glucose is and other substances are reabsorbed in the tubules. And that, of course, these reabsorption systems are saturable. You know, it's not indefinitely going, so to speak. But what is important is that you basically know the concept of clearance as the ratio between plasma concentration, urine concentration, and the volume of renal plasma flow. Don't worry if you don't get it straight away. We're going to have a whole workshop on this where you can exercise your abilities, and you're going to get it. So why do we care about clearance? Well, the truth is that it's really, really hard to work out the kidney function, especially in clinics, right? We can't do a biopsy of kidneys every time, right? So we need to find an easy enough way and accurate way to estimate the function of the kidneys. So, and the reason why we do that is because problems with kidney function can lead to loss of nutrients, failure to remove toxins. It may change the efficacy of a drug, and finally, last but not least, it will reduce the ability to regulate in the long and the midterm the blood pressure. So let's start from the glomerular filtration rate, which then will tell us, how we can measure clearance and how that is a measure of kidney function. So the glomerular filtration rate is the rate of freely filtered blood from the capillaries into the Bowman's capsule. Okay? Now, if a substance can freely go from the blood capillaries into the Bowman capsule, okay? Then if this substance is neither reabsorbed nor secreted by the tubules, and it doesn't have an effect on the metabolism kidneys, then at that point, the renal clearance of that substance will reflect the glomerular filtration rate, okay? So we don't have a way to directly measure the glomerular filtration rate. It's not like we can easily take samples of filtrate, yeah, and look at the ratio of different substances between the plasma and the filtrate. However, if a certain substance has the three characteristics I said, so freely filtered from the blood capillaries to the Bowman capsule, is not reabsorbed nor secreted by the tubules, and it doesn't affect the renal metabolism, so it doesn't accelerate or decelerate the renal metabolism, then we can conclude, we can infer that the clearance of that substance corresponds to the glomerular filtration rate. So, for example, substance that has these features is a polysaccharide, such as inulin, or creatinine, which is produced fairly constantly in the muscles. And creatinine, in fact, is usually, the ratio between creatinine in the urine and the creatinine in the plasma is typically used as a clinical estimate of the glomerular filtration rate. So if there's a problem at the level of the filtration, okay? In fact, the inulin clearance is directly related, and it corresponds to the glomerular filtration rate, because if the concentration of inulin is 1 milligram per milliliters in the blood, and then it gets fully filtered into the Bowman's capsule, then the concentration of inulin in the filtrate will be the same, okay? So inulin enters the glomerular filtration only, is not reabsorbed nor secreted, okay? So if I look at the concentration of inulin in the plasma and the concentration of inulin in the urine, where it gets obviously concentrated, then the glomerular filtration rate for inulin will correspond to the clearance of inulin, which is the ratio between the concentration of inulin in the urine and the concentration of inulin in the plasma times V, which is the volume of blood that arrives in the kidney per minute, which, for simplicity here is approximated to 1 milliliter per minute. So inulin, but at a clinical level, we actually use creatinine. Okay, after filtration, reabsorption and secretion occur. As we said, the elaboration of urine is the process which involves three sub-processes. Filtration, which occurs in the glomerulus, which is the filtration of blood plasma to form the filtrate, which then enters the tubules. This filtrate is also known as tubular fluid. Then reabsorption, not all the substances are reabsorbed. For example, inulin and creatinine are not reabsorbed, and is the movement of substances from the tubules to the blood. Or a substance can be secreted, so it can be actively moved from the blood into the tubules. So in summary, the clearance can be a good use, a good tool for estimating the glomerular filtration rate if we measure the clearance of a substance that is fully filtered, not reabsorbed, not secreted. So glucose is a very bad substance for measuring the glomerular filtration rate, because the clearance rate of glucose is 0 while it gets fully filtered. Then again, the clearance for sodium is around 0.9, for chloride is 1.3, for creatinine is 140, and then we have para-aminohypurate, which is a substance that we will use for measuring another kidney function, still using the clearance rate of para-aminohypurate. That is the effective renal plasma flow, or ERPF, effective renal plasma flow, which is a measure of renal function, and it can be found as a measure of clearance. Okay, so the clearance of a substance corresponds to the effective renal plasma flow if that substance is 1, freely filtered from the blood capillaries into the Bowman capsule, 2, secreted but not reabsorbed by the tubules, and of course doesn't increase nor decrease the renal metabolism. Repeat, the clearance of a substance can be used as a measure of effective renal plasma flow if it is freely filtered from the blood capillaries into the Bowman capsule. It is secreted but not reabsorbed by the tubules, and it has no other effect on renal metabolism. It's easy to understand, right? because then you have the two components. You've got of the blood that inputs into the kidney, the one that goes into the glomerulus, the one that goes into the vasa recta. Okay, so since the substance, is freely filtered and secreted, that will be a direct indication of the effective renal plasma flow. So the clearance of a substance that is freely filtered, secreted but not reabsorbed, and doesn't alter the renal metabolism correspond to the effective renal plasma flow. And this is the case of para-aminohypurate. Para-aminohypurate is freely filtered, is secreted but not reabsorbed, and it doesn't affect the renal metabolism. Okay. I'm not going to mention anymore what is the clearance. The clearance is the concentration of a substance in the urine divided by the concentration of a substance in the plasma times the rate of urine production in milliliters per minute. So the PA clearance, the para-aminohypurate clearance, corresponds to the renal effective plasma flow. Okay. So the renal plasma flow is the fraction of plasma through the kidney that is filtered. So the filtration fraction divided by the renal plasma flow. Okay. Sorry, then the filtration fraction is equal to the glomerular filtration rate divided by the renal plasma flow. In healthy organisms, the plasma volume is around 3 liters. The glomerular filtration rate is around 125 milliliters per minute, which means that the glomerular filtration rate is 180 liters per day. So the entire plasma is filtered and processed by the kidneys around 60 times a day, generating 1.5 liters of urine. So the glomerular filtration rate is actually tightly regulated. If it's not regulated, the kidneys may not be able to regulate the internal environment. So the changes in glomerular filtration rate can in particularly affect, amongst the other things, the concentration of sodium. And so the changes in tubular sodium is sensed and used to adjust the glomerular filtration rate. The neuronal control of the glomerular filtration rate from the sympathetic nerves, which regulate, of course, the arterial pressure entering glomerulus, affects, of course, the glomerular filtration rate, and so other hormones. In the third lesson, we will see actually how sodium is controlled and how these can lead to the regulation of the glomerular filtration rate. So, to sum up for this week, the urinary system consists in kidneys, ureters, bladder, and urethra. The kidney itself has 3 regions: the cortex, the medulla, and the pelvis, also known as hilus. The functional unit of the kidney is known as nephron, and it has many tubules and associated vessels. The unique characteristics of the epithelial cells in the tubular portion of the nephron allow each region to carry out the function, and it's usually a brush border, and this function is mostly reabsorption and secretion. The step 1 of the urine production is the filtration in the glomerulus. So 20% of plasma is filtered into the Bowman capsule, and then the tubular fluid gets collected into the proximal tubule. In the step 2, in the proximal convoluted tubule, there is the obligatory reabsorption of all filtered glucose, amino acids, sodium chloride, and bicarbonate, and that's where the process of secretion takes place. In the step 3, the loop which occurs in the loop of Henle, that's where the osmotic gradient is created by sodium chloride reabsorption into the interstitial fluid, while the tuck junction prevents the movement of water. The step 4 into the distal convoluted tubule, that's where we regulate the absorption secretion of ions and of water. 5, in the collecting duct, the antidiuretic hormone works and is released if the osmolarity is more than 290 milliosmol per liter to regulate the water loss. So it's both a summary and how can I put it? Spoiler of what is to come. We will go through once again in much more detail, but this is just to give you a taste. So the key points: learn the structure of the kidney, both at a macroscopic and microscopic level. Try to understand the structural organization of the nephron and how this allows it to carry out its function. Understand why it is important to have the proxy measures for renal function and how the clearance of creatinine and paraminohyperate will allow you to measure glomerular filtration rate and effective renal plasma flow, respectively. Very important. You will have to be able to explain with examples how this would be measured, both the glomerular filtration rate and the effective renal plasma flow. I will stress this until obsession. You need to know these things. And if you want to know more, of course, always make reference to your textbooks or drop a question in the thingy or in the Padlet. And see you next time. Bye-bye.